Good afternoon, Internet. I'm Matt Buyak, and in this video I'll be looking at a procedure for generating primitive Pythagorean triples. So you might recall in the last video we had just finished up problem number 8 in the Project Euler problem archive. But if you look ahead to problem number 9, you'll see that it involves the generation of Pythagorean triples. And so we really need a technique for doing that before we can tackle that problem. And I think I first encountered the procedure for doing this about 15 years ago. And at the time, I didn't really understand why the procedure was what it was or how it had been discovered. I could do the algebra to show that it was correct, but I felt like I was missing that eureka moment where you feel like you've gained some deeper understanding. And so rather than just Google the procedure, I decided I would try to tackle this just like I would any other number theory problem. And that perhaps by sharing that investigation with you, maybe you could gain a little bit of insight into how we solve Diophantine equations like this. That is, those equations with integer solutions. But also maybe even give you that same eureka moment where you feel like you've gained some deeper understanding. So let's get into it. We'll open up in Emacs. We'll have this Pythagoras.txt. So as you recall from the solution or the question, we're looking for solutions to this equation. And in particular, we're looking for solutions where A, B, and C share no common divisors. And the reason that is, these are what we call the primitive Pythagorean triples, is that if A, B, and C share a common divisor, call it D, then we can see that that by dividing the entire thing by d squared, we get another solution, which is also a Pythagorean triple. And so we're really only concerned with the primitive Pythagorean triples. You'll note that from a Pythagorean triple, a primitive Pythagorean triple, we can generate an infinite number of non-primitive triples just by multiplying by d squared. So that's the first point of note. Second, when we first start examining an equation like this, you can often get quite a bit of mileage just by looking at what variables can be even and what variables can be odd, and what the relationships between those are. So in particular, if you were to imagine that A and B are both even, you'll note that the square of an even number is another even number, and the sum of two even numbers is an even number. And so C squared, and therefore C, would also have to be an even number. But this violates our stipulation that we're only concerned with primitive Pythagorean triples, because then A, B, and C would all be divisible by 2. And so we can conclude that either A must be odd or B must be odd. And you'll notice that the square of an odd number is an odd number. And like I said, the square of an even number is an even number. But then the sum of an even number and an odd number is an odd number. And so regardless of whether A is even and B is odd or vice versa, C, we know, is odd. So we'll just note that down here. Okay, so the next thing that came to mind when I was examining this is to rearrange the equation as follows, to write it instead as the difference of squares, like so. And that's because we can factor the difference of squares, and often that will give us a lot of information about the possible solutions to a problem like this. And so, so I got to this point, and it wasn't obvious to me how to continue farther. And so, one common technique in mathematics is if you can't find a way to make progress by looking at the general problem, you can try looking at a more specific case and see if you can find a solution in that case. In particular, I looked at the equation 7 squared is equal to c minus a times c plus a. And the idea is that if you are able to find a solution to a more specific case like this, then you can ask yourself why that particular case had a solution, and maybe come up with some conditions that will give you a hint for what other cases might have solutions, or what other cases might not have a solution. So from this point, we can, as I mentioned, since we've factored this, we can look at the factor pairs of 7 squared and see if we assign, one member of each pair to c minus a and the other to c plus a, we might be able to come up with some solutions. So we have 7 squared is equal to 49, and that's equal to either 1 times 49 or 7 times 7, and those are the only factor pairs. So so if we suppose c minus a is equal to 1 and c plus a is equal to 49, that's just coming from this first factor pair. We can try to come up with a solution by solving for c and a. So just by adding these two together, we get 2c is equal to 50, and therefore c is equal to 25. And then we can solve for a, and we come up with a is equal to 24. And so we can pull up our calculator real quick to just double check that this is in fact a Pythagorean triple. So if we do 7 squared plus 24 squared, and then we take the square root of that, we get 25 as expected. So that is our first Pythagorean triple. Now you'll note that if we try to do the same with the second factor pair, we run into a little bit of a problem because we conclude that a has to be equal to 0. And the problem with that is that we've already stipulated that these have to be natural numbers. That is, they're greater than 0. And so 7 squared does not, or 7 times 7 rather, does not correspond to a solution. So let's think about what conclusions we can, or lessons we can draw from this particular example. The first one is that given a factor pair, we can, in some cases, solve for a and c to get a solution to our problem. But that if we factor b squared as b times b, then we do not get a solution. So it might be worth generalizing at this point. If we suppose u equals c minus a and v equals c plus a, then if we want to solve for c, we could just add these two together and divide by 2. So that's u plus v over 2. That's going to be equal to c. And similar, we can subtract u from v and divide by 2 and get a, like so. Let's just reorder that. And one thing that immediately jumps out to me when I'm looking at this is that this has to be even. That is, v plus u or v minus u has to be an even number. So that in particular, we can conclude that either u and v are both even, or u and v are both odd. And that's because if one of those were even and the other was odd, we would have an odd number. And therefore, this wouldn't be divisible by 2, and it wouldn't correspond to a solution. Okay, so after this, I wanted to try a number that was a little bit more interesting. 7 is prime. It only has one prime factor. And so it's not a particularly interesting case. So let's now try instead something with... I'm going to try an even number and also a number that has more than one prime factor, and that's 6. So we can list out the factor pairs of 6 squared. So if we have 6 squared is equal to 36, that's going to be either 1 times 36 or 2 times 18 or 3 times 12 or 4 times 9 or 6 times 6. But as we mentioned before, we know that 6 times 6 is not going to correspond to a solution. But then as we look at these other factorings, we notice that for almost all of them, one of the 2 factors is even and the other is odd. But we already concluded up here that they have to be either both even or both odd. And so in particular, we see that 2 times 18 is the only factor pair that doesn't violate that requirement. And so now if we say, u is equal to 2 and v is equal to 18, we can calculate that a is equal to 18 minus 2 over 2, which is 8, and c is equal to 18 plus 2 over 2, which is equal to 10. So this gives us our second Pythagorean triple. But you'll notice that so our triple 6, 8, 10 is not primitive. We can divide all 3 of those by 2. And so that does not, even though it met our other requirements, it does not actually give us a primitive Pythagorean triple. So, so from this point, I was trying to think of a way to avoid generating these sort of bad pairs where one of the factors is even and the other is odd. And one thing that I came up with is that if our number b is odd, then it's necessarily the case that both factors are odd, which would meet our requirements. And furthermore, because a squared and b squared are symmetric in the original equation here, so up at the top here, we can assume that b is the odd one and a is the even one, because we know that one of them is even and the other one is odd. And so we can just assume that b is the odd one, which fixes our problem of generating factor pairs that where one is even and one is odd. So now we can say, assume b is odd. And that's without loss of generality is the acronym that I'm using there. Okay, so let's, now that we're limiting ourselves to odd values of b, let's try one more interesting value, just to give us a little bit more insight. So just grab this expression, and let's consider 15 instead. So if we look at the factor pairings of 15 squared, then that's going to give us, 1 times 225 is equal to, let's see, 3 times 75, I believe, is equal to 5 times 45 is equal to 9 times 25 is equal to 15 times 15. But again, this one is not allowed, so we're not going to consider that one. So let's take a look at this first one here, 1 times 225. So we'll say u is equal to 1, v is equal to 225, and that's going to give us a is equal to 112, c is equal to 113. So that seems to meet all our requirements. Let's double check to make sure that is in fact a primitive Pythagorean triple. So we'll have 15 squared plus 112 squared. I seem to have, I made a bit of a typo there. I took 112 to the 112th power. That's not what we want. So we'll say 15 squared plus 112 squared, and then we'll take the square root of that, which is 113 as expected. So that gives us our third Pythagorean triple and second primitive Pythagorean triple. So then we might go through and look at the rest of these and see which of them correspond to Pythagorean triples. And what you'll find is that this last one here does, and these middle two do as well, but not primitive Pythagorean triples. And from looking at this, you'll notice that for each of these two, the 3 times 75 and 5 times 45, the two factors have a common divisor. And for the other two pairs, 1 times 225 and 9 times 25, not only do they not share a common divisor, but the factors are both squares. And so we might want to investigate farther whether that's always the case and maybe why that's the case. So let's suppose that we have u is equal to ps and v is equal to pt for some prime p. So then we can look at the equations for c and a, and so we'll have a is equal to what was that? Pt, or rather v minus u over 2, which is equal to pt minus ps over 2. And you'll see that we can factor out this p here. And likewise, we can say c is equal to v plus u over 2, which is equal to p times t plus s over 2. So yeah, so if p is an odd prime, we've already noted that u and v both have to be odd, and so we know that p is not 2. It's not the even prime, and so because p is an odd prime, we know that 2 must divide t minus s and t plus s, and therefore a and c have a common divisor of p. And we've already said that in order to be a primitive Pythagorean triple, we can't have common divisors like that. And so we conclude that in order for our solution to be a primitive Pythagorean triple, u and v also must share no common divisors. Now it turns out it actually follows directly from that u and v must be squares. And we can see why that is by looking at one final example. So let's suppose b equals 105, which is equal to 3 times 5 times 7. I specifically chose that as the product of the first 3 odd primes. And so now we might look at the factor pairs of 105 squared. And you'll notice something here in a moment. So in order for the two factor pairs to have no common divisors, we have to assign each prime to either the first member of the factor pair or the second. So you'll see how this goes. Let's suppose we have 3 squared times 5 times 7 squared is equal to 3 times 5 squared times 7 squared. Oh, I've my apologies. I've forgotten one at the beginning here. We have 1 times 3 times 5 times 7 squared, and that's actually all of the yes, that should be all of the possible factor pairs, such that the two factor pairs or members of the factor pair have no common divisors. And you can see that in fact they're all squares. And so this suggests the one final piece that we need in order to have our solution. We've already noted that u and v are both odd and that they have no common divisors. And now we've determined that also that they must be squares. But the process of taking b squared and factoring it and finding these factor pairs of u and v can be computationally expensive, especially for large values of b. And so we'd much rather do it the other way around, because while factoring is computationally expensive, multiplying 3 numbers together is trivial. And so rather than starting with b and trying to find u and v, we can just start with u and v and find b. So let's suppose u equals n squared and v equals m squared. Let's see, with GCD of n and m equal to 1. And you'll notice that if n and m have no common divisor, it's also the case that that u and v have no common divisors. You'll also notice that in order for u and v to be odd, n is odd and m is odd. Okay, so now we can check to see that in the general case, this does in fact give us our solution. So if we say, we already have our equation for a equals v minus u over 2. And so that's just going to be, oh, excuse me, I've got these backwards. I want to keep the alphabetical order consistent. Yeah, so then we'll say that is equal to n squared minus m squared over 2. We'll say c. Let's do b first. is equal to, you'll recall that b squared was equal to, we have b squared is equal to u times v is equal to nm squared. So then we can just take the square root of both sides and find that b is equal to n times m. Similarly, we can calculate c, and we get v plus u over 2 is equal to n squared plus m squared over 2. So now we have our procedure, and now we can check to make sure that it actually does work as intended. So we take our expression for a here, and we say a squared plus b squared. That's going to be equal to this expression here, plus nm squared. Oh, excuse me, I didn't actually square that. Okay, so now we can expand this out. So we'll get n to the fourth minus 2 nm squared plus m to the fourth divided by 4. And we want to combine this term with this expression here, and so we're going to multiply that by 4 and also divide it by 4. And so now you see if we combine these two, we get our same expression here, except for this middle term we have minus 2 nm squared plus 4 nm squared. And so we'll just have plus 2 nm squared. And then we can factor this to give us n squared plus m squared over 2, and then that whole thing squared. But that's just equal to c squared, as expected. So now we have our procedure. We've checked that it's correct. In the next video, we'll take a look at problem number 9 and apply this method to solve that problem.